Okay, so in the name of Allah, the most merciful and most beneficent, today this is our second lecture in the track of pure mathematics. And in the first lecture, we discussed mathematical logic, or what we call the basic elements of mathematical thinking. From today, or in particularly today's session or lecture, we are going to discuss real analysis. So, if we see the whole course of real analysis, it's very huge, and we must have 3 to 4 weeks to complete this. But since we are trying to complete it within 1 or 2 weeks, so we should be as concise as possible. So we have to shorten the things basically to cover up the syllabus within short time. So I will not discuss the construction of the basic elements of real analysis like set of natural numbers, set of integers, set of rational numbers, and set of real numbers. Otherwise, when we start this course, we must discuss how these numbers are being constructed. But we will take the number sets as they are, and we know them, that what is a set of natural numbers, what is a set of integers, and so on. Otherwise, we can construct these numbers in a mathematical way. That why natural numbers are 1, 2, 3, and so on. Why the integers are some sort of negative and positive whole numbers. Why the rational numbers are in the form of p by q. And why there is need to introduce such a set. Similarly, why real numbers. And what is the main difference between reals and rationals. So, but we can discuss a little bit that natural numbers are basically counting numbers. So the first thing is that we are discussing number sets a bit. The first set we have is a set of natural numbers denoted by this n, and that's this set. Now we can also ask a question that what does 1 represent, what does 2 represent, what does 3 represent. But we know these sets, so we are going to use these sets as we know. Otherwise we can discuss the construction of this set, but it will take a lot of time. And whenever in this course I use this symbol and not, it means I have this set. In some terminology this is called set of whole numbers, but we'll call it set of natural numbers, because in some context we will be using 0 as well, but we will call it the set of natural numbers with 0. And this is set of natural numbers without 0. So this is set of natural numbers, we know this thing. Now the second thing is set of integers. That is simply I can write 0 and positive numbers on the right and negative numbers on the left. And if we have this set, why there is need to introduce a new set? The main reason is we don't have the additive inverses of these numbers. It means if I have a number 3, what should I add to this number to get a null element that is 0? So that number is basically minus 3, but this minus 3 does not belong to the set of natural numbers. Hence we introduce a new set, what we call set of integers. So this is that thing what we call the set of integers with positive and negative whole numbers including 0. And we can also define some algebraic structures on these sets. We know very well that this is I think an abelian group with respect to the operation addition. So I say that this z along with this plus operation is an abelian group. And we should not be able to, or we are not necessarily required to understand this concept right now. We will be doing it later on. Okay, so the next thing is, when this set is not okay, or what are the conditions that we are not okay with this set?
Multiplicative inverse.
It is simply the multiplicative inverse.
Yes, sir.
for a number, let's say 2, I should have some element in this one so that the result becomes the multiplicative identity, and that number is 1 upon 2, which does not belong to the set of integers. Hence we introduce a new set, what we call set of rational numbers. And set of rational numbers, we know very well, is all the numbers of the form p by q, where what happens?
P and q integers.
P is an integer, q is an integer, but it is except 0. So this is integers, and I have taken out the 0 element from the set of integers. This is called the difference in the sets, you know very well. Difference is denoted by a minus b or a slash b. Both are okay. So if we take this set, we can find out the multiplicative inverses of all the non-zero elements.
Yes, sir.
Multiplicative inverse of 1, 2, 3, 2 by 3, 3 by 2, and so on, but there exists no multiplicative inverse of 0. Now we are okay with these all the sets, set of natural numbers, set of integers, set of rational numbers. Then why we need another set, what we call set of real numbers? Why there is need of such a set?
Square root.
Yes. So there are so many reasons to introduce such a set. We can define so many algebraic structures on integers, and we can also define some algebraic structures on this Q as well. And I think this Q, along with this addition operation, is an abelian group. And this Q, except I think element 0, with multiplication is also abelian group. And this Q, with these both operations, is a field as well. And we know very well what are field properties.
Yes, sir.
So it is similar to ring. Okay, so if we have these three sets, some mathematicians agree that we are okay. We don't know the set of, we don't need the set of real numbers. But there are some things that we need the set of real numbers to be dealt with so many problems. The first thing is that this set is not complete. This is one reason. This set is not complete. It means if I take a number line, then each and every point will be a rational number, but still there would be some gaps where you cannot define a rational number.
Yes,
it means if you take this rational line, there would be gaps in this one.
yes, sir.
And if you take this line of integers, you have only numbers here.
Yes, sir.
Like you can say this is 0, this is 1, this is 2, this is 3, minus 1, minus 2, minus 3. Now this line has huge gaps, and the gaps are only you have numbers here.
Yes, sir.
In between there is no any integer. It means you have these as gaps. So huge gaps are there, huge gaps. But here there are gaps, very small gaps, but there are gaps.
Yes, sir.
So to fill the gaps, you introduce a new set, what we call the set of real numbers. So to fill that gap, we always need a new number, what we call the set of real numbers. This is the one reason. The another reason is this set is not complete. It means there are some sequences which we will see later on which do not converge in Q. There are some sequences which do not converge in Q. This is the problem, that's why we introduce a new set. And we call those sequences to be Cauchy sequences. So Cauchy sequences do not converge in the set of rational numbers. This is again another problem. The third problem is, this is the first problem, this is the second problem. We will discuss this problem in detail. We will not discuss this problem, but you can understand that there are gaps.
Yes,
if I say you to graph the value of square root of 2 on this line, then you can always show me, but square root of 2 is not a rational number.
yes,
But still it will be some value over here on this line. But at this point there is no rational number, it means there is basically a gap over here. So this is another reason, and we will be discussing this thing in detail. The first thing is that let us introduce sequences,
Yes, sir.
what are convergent sequences, and so on. What is the third reason we don't have solutions? Has no solutions in Q. It means I claim that give me a number, when I square that number the answer should be 2.
2.
So there is no rational number so that I square that number and the answer comes to be 2. It's not possible. So this is the third reason that why we are going to introduce a new set, the set of real numbers. And what is set of real numbers? It is basically this set rational numbers and some other numbers which are not rational.
Not rational.
And we call those numbers to be Q prime. It means the set of irrational numbers.
Rational number.
So this is a short discussion that what are these sets and why do we study. Now if you apply these properties on set of real numbers, exactly you can copy the properties. Set of real numbers with plus operation is an abelian group. Set of real numbers except 0 with multiplication is also an abelian group.
Yes, sir.
And this replaced with R is also a field. But there is some additional structure that we can define on this thing. What we call this set is complete. Every Cauchy sequence converges in this set.
Yes, sir.
And there are no gaps in the real line. And we have solutions for this type of equation in the set of real numbers.
Yes, sir.
That's why we need this set when we are going to study real analysis. There is another set, what we call the set of complex numbers. But since we are studying only real analysis, so we are restricting ourselves to the set of real numbers. Okay, so
means radical 2 is not lying in this line, basically in rational line.
it does not lie on rational line, but if we consider this a real line, then it lies on that line. Basically, this number lies on this line, but at exactly that point there is no rational number. It means there is a gap in this cube. But this number lies on real line, we know very well. And we know very well how to graph this line, this number on this type of line. We always teach our students. I think you know very well that thing. Okay, so we can discuss the construction of every set, construction of natural numbers, integers, real numbers, and we can also define the operations on them, like why addition is defined in the way it is. Why 1 plus 2 is 3 and 2 plus 2 is 4 and 2 plus 3 is 5 and so on. But this is very basic structure. I will suggest you some notes and some exercises you will see and you will find the construction over there. It's not a big deal, it's very easy. So let us begin the traditional things on this course. These were some sets that we need in this course: the set of natural numbers, the set of integers, the set of rational numbers, and the set of real numbers, and the basic algebraic structures on those sets. The main purpose of this course is to study calculus in a rigorous way. We know very well that thing. Calculus means it can be single variable calculus as well as multivariate calculus. But the first thing is that our main goal would be to discuss only single variable calculus, and we can extend it to the higher case. But to discuss calculus in a more rigorous way, like discuss limits, differentiability, continuity and integrability, we always need to define some fundamental structures. So we always start from what we call sequences. So we are going to define what a sequence is, then we are going to define some extra structures on sequences. So what is a sequence? Any idea?
Set of number which is Which form a definite rule, which is formed on definite rule.
Okay, and
Sequence is actually a function
a function.
whose domain is actually the natural numbers.
Natural
Ring can be real or complex.
Yes. So it's basically a map. A map, I call it the map to be, let's say, AN, and the domain of this map is the set of natural numbers, and is the range is the set of, or codomain is the set of real numbers. So it's a map, it's a function. We know very well what a function is, whose domain is the set of natural numbers, and the codomain is the set of real numbers. Sometimes I will introduce this notation in this one, and I call this notation to be the set of all natural numbers including 0. So this is a map which takes any number from the set of natural numbers and spits out a real number. And what are the notations? Each and every element from this set can be represented in the form of a set. We call it A1, A2, A3, up to so on. And we call this set a countable set. What do you mean by a countable set?
Whose cardinality is findable. Cardinality.
We have the basic ideas.
Okay. Countable set is that actually whom we can actually map with the natural numbers. Actually.
Yes, there is one correspondence.
Between.
But it's very good, but let us make it a bit simple.
Thank you.
Finite and infinite sets, we know very well.
Yeah.
Finite is whose cardinality is finite,
Yeah.
and infinite set is whose cardinality is
Infinite.
infinite. But this is not finite or infinite. This is countable or uncountable set. Let me give you an example. If we have a set 1, 2, 3, and so on, this is infinite. We know very well.
Alright.
Because you cannot count all the elements. But this is countable. And what do I mean by countable set? If you take any space, let's say this is 100 and this is 101 and so on. I am fixing the domain from this one to this one. Can you count these?
Sure.
From 2 to 100, how many numbers?
100 minus 2, 98.
99.
99.
So, if you have a countable set, you start from some point, you end at some point, you can count the elements within those ranges from the beginning and the end of the range. If you can count in that range, we call that countable.
Countable set.
But if I give you this real line, this is 0, this is 1, this is a real line, the minus 1, I say you to count the real numbers between 0 and 1.
Impossible.
Impossible, because you can't count every real number.
This makes sense.
You can't count this every real number in this. Hence it is uncountable,
Lesson.
and this is countable. The set of natural numbers is countable. The set of integers is countable, because you can take some interval and you can count what lies in between. Set of rational numbers.
Not
Countable.
Set of rational numbers.
Uncountable.
Countable.
For instance, 2 to 4.
Rational number is this.
Okay.
What is A?
A and B are integers.
Integers.
A is integer.
B
B is integer.
Yes, sir.
A is countable. B is countable.
Therefore,
Their comparisons
are also
will be countable. Always. Always.
Can you draw this picture?
This picture can't be drawn. This picture is okay. You are okay with this.
okay.
But this picture is not possible. But if I give you, like, if I give you integers, let's say from 1 to, let's say 5, 2, 3, 4, 5. How many integers? 1, 2, 3, 4, 5.
5.
1, 2, 3, 4, 5. How many integers? 5. And when you find their orders, like this number would be, let's say 1 upon 1, 1 upon 1. This number would be 1 upon 2, this number would be 1 upon 3 and 1 upon 4. So how many rational numbers would be in total?
Just like Cartesian product is there.
Yes. It means if you restrict your domain of integers from 1 to 5 for A, if you restrict your domain of integers from 1 to 5 for B, let's say, then how many combinations you can find out? 1 with 1, 1 with 2, 1 with 3, 1 with 4, 1 with 5, 2 with 1, 2 with 2, 2 with 3 and so on. So how many are there?
25.
Countable. So set of rational numbers is also countable. Even there are so many rational numbers within some interval, but still those rational numbers are countable. This is not the good explanation for countability of rational numbers. You can go for some, when you construct rational numbers, you say that rational numbers are some sort of equivalence clauses on integers. Since those are equivalence clauses on integers, integers are countable, rational numbers will be countable. So you can give that argument.
Somewhere that I have seen the things that when we are given the two set, and I can count their elements, how many, the function for be there, 1, 1, so on.
It's very basic thing. I will share some notes with you. You can find out how many functions in total, how many relations in total, how many one-to-one functions in total, how many on-to functions in total. So you can find out these functions from a set with some elements, let's say m, to another set, let's say elements n. You can find out. I will share this thing with you. But you can discuss this thing, but it will take a lot of time. So this is notation for a sequence. We can also denote it with only an. We can also denote it with an when n runs from 1 to infinity. And there are lots of notations for a sequence. And we'll also use this notation an when n belongs to the set of natural numbers.
So you are writing your A1, A2, what does it representing?
A1 is the first term of a sequence, A2 is the second term of the sequence, A3 is the third term of the sequence. You have these all the terms enclosed in a set, we call it a sequence. And we can also denote only with an or an when n goes from 1 to infinity, or an when n belongs to the set of natural numbers. These are different notations for a sequence. We can also give some other notations, but these are very fundamental.
So again, irrationals are also countable?
Irrationals?
No.
Because reals are uncountable.
Reals are countable. Reals
Set
are,
of real numbers,
are uncountable.
uncountable.
Yes.
Real number is union of q and q complement.
Yeah.
Q is countable, q complement would be uncountable.
Yes.
If q is countable, q complement is countable, their union will be countable.
Okay.
So reals is not countable, so it's a problem. It means, as the traditional example is given, that how do you compare rationals and irrationals? So if there is an ocean and you have a big ship like Titanic, so your Titanic ship is the set of rational numbers and the whole ocean is the set of irrational numbers. So which set is bigger? Irrational. If we see irrational numbers are square root 2, square root 3, square root 5, e and pi, okay, these are irrational.
No, but
But
that's
there are uncountable numbers and the set of rational numbers is countable. So I gave you a basic example there. What are rational numbers? This is a ship like a Titanic and the whole ocean is a set of rational numbers.
It means a real number is uncountable.
Real number is uncountable, set of real numbers. Okay, so let us take some examples in this one. I am going to erase this one so that we may discuss more and more examples as we can for sequences. The first example is 1 over n. What is going to be the first element or the first term in the sequence?
1,
You will put n is equal to 1, that would be 1, and then 2, 1 by 2,
1 by
1 by 3, and so on. So algebraic way to write the sequence is 1, 1 by 2, 1 by 3, and so on. And what is the geometric structure? Where does 1 lie? Corresponding to 1 lies here. Let me put it here. 1 lies here.
1 1.
And then
1 half.
this is 1 half, and then this is
1 third.
1 third, and then this is
1 fourth.
and then 1/5, and so on. This is example number 1. Let us take another example. N equals n. What is the first term?
1,
Second,
2,
3,
4,
and so on. So if you plot 1 and then 2, 3, 4, and so on. The third example is n equals minus 1 power n.
minus 1,
So minus 1,
2,
when you put 2 here it would be 1,
1.
minus 1,
1,
1, minus 1, and so on. So how do you plot these things? What is the first element?
minus 1,
Minus 1 out.
Minus 1, it means here.
G,
What is the second element?
1, 1,
1. Third element? Minus 1. Fourth element? 1. It means you go,
oscillating.
yes, you go down, then you go up, then you go down, then you go up, and so on. The next example is n times minus 1 power n.
Ah,
N times minus 1
over n.
power n. So if you put 1 here, that would be
minus 1,
minus 1.
Yes, sir.
2 here would be,
Positive 2.
positive 2,
so this is positive 2. Then
3.
negative 3.
Negative
This
3.
is negative 3. Then
positive
positive 4.
4.
So it would be this positive 4. So you have this sequence.
Yes, sir.
So I have put basically 4 examples of sequences, and we want to discuss something special related to these 4 examples. Can you see what is the difference between these 4 examples that I have written so far?
Yes, sir. One is increasing. Neither increasing nor decreasing.
Either increasing nor decreasing,
Same.
increasing and decreasing.
increasing and decreasing, both. It increases in
Yes,
this
sir.
way, it
Increasing.
decreases in this
Decreasing.
way. But we are not interested in increasing or decreasing.
Yes, sir.
We want something else. Okay, so what happens in this one, that if I take my whole region of these numbers, let's name this set to be x. What happens, these elements in this set are taking some sort of quasi way, then they are going to approach a fixed number.
Yes, sir.
What happens? The number is 1, then 1 upon 2, then 1 upon 3. When you go along this path, these all the numbers are going to approach a fixed value.
Yes, sir. Yes, sir.
For example, after 1 millionth or let's say 1,000 times, what happens? You get
0.0000.
1 upon 1,000, that is 0.001.
Very good.
And if it is 1 by 10,000, it is 0.0001. So when you go along this sequence, you go near to a fixed value.
Yes, sir.
What is that value?
0.
0.
0.
So you can see your sequence keep on decreasing and you reach a fixed value finally, that is 0. You go near to that value, you don't reach. You go near to that value. What happens in this case?
Undefined.
1, then 2, then 3. It means when you take set x, your terms of sequence are in this way. Then 1, then 2, then 3, and so on and so forth. They never go near to a fixed value.
Yes, sir.
What happens in this case? You have only two outputs. One is -1, other is 1. So what happens? Your first term is -1, second term is 1. -1, 1. -1, 1. They again never go near to a fixed value. They take two different values, but they never go near to a fixed value. What happens in this case? Again your function takes different values but in different direction. One direction goes in this way. Okay, first here, then here, then here, then here. So your function or a sequence takes two different values, but they are going away from each other when you go along that sequence. So why I have written these four special examples when we discuss sequences? What happens in this first example?
Our sequence
Convergent.
is converging to
Convergent.
some
Yes.
Converging, yes, sir.
We say that our sequence goes near to 0. As we go along this sequence, we say that this sequence is
Convergent sequence.
convergent. And what is the limit of this sequence?
0.
With the limit 0. And we write this as our sequence n goes to
L.
0
0, yes, sir.
as n goes to infinity.
Infinity.
This is one notation, or we can also write limit an equals 0
when
as n goes to
infinity.
infinity.
Wow.
And why this happens? Because our sequence goes near to a fixed value as we go along a sequence,
Yes, sir.
or as we increase the number of terms.
Comes.
You can see 1 by 2, 1 by 3, 1 by 4, and so on. What happens in this case?
Increase. Diverge.
Both infinite.
Diverge.
Because this sequence to be not convergent,
Not convergent.
we'll introduce divergent
Yes, sir.
later on.
Later.
This is not converging.
Not
Can
convergent.
we write this in this way? Just
We cannot say this thing in this way, because this thing is not same as this. We can apply this whole idea into this definition that our sequence goes to a fixed value 0, and this fixed value can be any limit, but this limit should be finite. As we increase the number of terms, we can't say in this way, because our sequence explodes to
infinite.
positive infinity. So what should I write here? I am writing here 0, I can't write here infinity.
Means the sequence is definitely.
This is a definition of convergence. We'll define divergence, then we'll say, okay, what is this? Right now we are saying this is
Not
Not
convergent.
convergent.
not convergent. What about this?
This takes actually two values.
Two values, so again,
Not convergent. Async.
not convergent.
Not a unique way.
And this is also
Not convergent.
not convergent. We can name them something else. So let us name this thing be divergent to positive infinity. We'll see later on what do we mean by divergent to positive infinity.
Yes, sir.
And what do we call this thing?
Good thing?
Divergent.
No.
Oscillating.
So this thing oscillates
Between.
finitely between 1 and minus 1. Oscillates
Yes, sir.
finitely, it means takes 1, minus 1, 1, minus 1, between two values 1 and minus 1. What do we call this?
Oscillating infinite.
This thing also oscillates. This thing oscillates finitely, but this thing oscillates
Infinitely.
infinitely between positive infinity and
Negative infinity.
negative infinity. Because what happens in this sequence, you will get these terms minus 1, 2, minus 3, 4, minus 5, 6, minus 7, 8, minus 9, 10, and so on. If you see these odd numbers, these are divergent to negative infinity. If you see these even numbers, these are divergent to positive infinity. So you are basically diverging in both directions, positive infinity as well as negative infinity. So we call this thing oscillates infinitely between two values, positive infinity and negative infinity.
So can't we say we are converging to the infinite? Especially you are using the word diverge for infinite.
We say when a sequence is convergent, it means it approaches to a fixed value,
Yes.
which should not be infinite.
Yes, sir.
When we say infinite, we can't use the word convergence.
Yes, sir.
We use the word divergence. Okay, so the thing is that how can we define convergent sequences mathematically? This is the good thing. So in this course, basically every example and every definition will be regarded as one MCQ in any of your examinations that you are going to appear. So we have discussed what is a sequence. We have discussed 4 sequences. One was convergent, another was not convergent.
Yes, sir.
The remaining 3 were not convergent, but we also classified them. One was divergent to positive infinity, one was oscillating finitely, another was oscillating infinitely. Yes.
Convergent only was about divergent.
हाँ divergent ये सामने दिखाना है पर divergent में पूरे types हैं देखिए ये सामने oscillate दिखाना है oscillates finitely, oscillates infinitely. There are different cases in that. It's not always divergent. Even in divergent we have divergent to positive infinity and divergent to negative. We have 2 cases in divergence. But for now we are only interested in which sequences are convergent. So what should be the definition of convergence mathematically? How do we define a convergent sequence? So what happens that my sequence can take different values, but I say this sequence is convergent. It means in long run the terms of my sequence approach to a fixed value A, which I call the limit of this sequence, or the point where our sequence converges. So what happens that the first term of sequence is here, the second term is here, then here, third, fourth, fifth, sixth, seventh, ninth, tenth, whatever. After maybe some sort of 1,000 or 10,000 or 1 million terms, the term in my sequence goes very near to this fixed value A. After maybe 1,000 terms or 10,000 terms or 1 million terms, that term of my sequence goes very near to that fixed value A. But it never approaches it. It goes very near to that fixed value. One traditional example that we might give in our classes, okay, this is a distance from this wall to this wall. Every time I say you to cover half of the distance. So what you will do, you will start from here and you will reach at the center. Then this is the distance left. I say you to cover half of the distance again. Then you reach here. Half of the distance again, then here. So you will cover half distance each and every interval, but you will never reach the wall. You will go closer and closer and closer to the wall, but you will never reach it. So this is the same idea. So how can I say that the terms of my sequence go very near to that fixed value A, and after 10,000 terms they go near to A, maybe after 1 million or 10 million terms again they will leave A and they will go another direction. This is a thing that I have to define mathematically, that when they go near to this fixed value, I define some parameter for nearness, something for nearness. Okay, this is the fixed value A. I define my nearness. Okay, my nearness is this boundary. My nearness is like airport city. My nearness is this mohalla. My nearness is this 10 meter distance. So I'm going to define my
Nearness.
neighborhood or nearness. So I call that nearness to be a ball or an open circle or open ball with radius epsilon or r. So this is my nearness or my colony or my city or my mohalla. And when someone comes in my mohalla, I can say that that sequence converges to fixed value A, and that value is me, myself. So how can we define this thing mathematically? This is what we call convergence. But we have to define this thing mathematically. It means that for all epsilon positive, it means the radius of your nearness should be something positive. And for all epsilon means whatever radius you take, your mohalla can be small and can be big, your colony or your city. So that epsilon shows the radius of your city. For all epsilon positive, what happens? The distance between the terms of sequence, it means these terms. Let's say this term and this fixed value. This is term of your sequence an and this is fixed value a. Its distance from a should be less than the radius of the circle. What is that? Epsilon. So whatever epsilon you take, whatever neighborhood you take, now this neighborhood will be taken as small as possible because you want to define convergence. I cannot define that my neighborhood is this whole world. If someone comes in this world, he is in my neighborhood. No. You will take as small neighborhood as possible. When you define convergence, you take epsilon as small as possible. When you define divergence, you take a value which is as big as possible. We'll come to that later on. As small as possible, what happens? The difference between the terms of sequence and your limit, this is not difference but this is distance. And we define this distance in Euclidean metric. We can define distance as another matrix by generalizing and writing only d. D means distance. Should be less than the radius of my epsilon neighborhood or mohalla or whatever. When this happens, so I have to define something additionally then that when this thing should happen, I have to give this n a value. After 1000 terms it should happen, after 10,000 terms it should happen. You should give a fixed value. So I say that for all epsilon there exists a fixed value n from the natural numbers. N is a fixed value. We call this value to be, let's say 10,000 or 1 million or whatever. That whenever you take any n beyond this fixed value n, then this happens. This is what we say the mathematical definition of convergence of a sequence to a point A. It means there is a fixed value n, it should be let's say 10,000, that after 10,000 terms, this n small n means after 10,000 terms, 10,001, 10,002, the difference between this and this should be smaller than your given epsilon. Let us discuss this thing in the context of this example. I say this sequence converges to 0. Can I define the same thing mathematically? I say for all epsilon positive, it means you will give me a neighborhood. You say that okay, your sequence converges to this 0. You take the epsilon to be as small as possible. Take epsilon to be 0.001. This is your epsilon. It means in your neighborhood 0, you have defined a radius. What is that radius? 0.001. This is your neighborhood. And you say that do your sequences reach in this neighborhood? I claim that they reach, and when they reach, you say your sequence is convergent. Now you have to give me this. For all epsilon means you can give me any epsilon. There exists this means give me this value. So what n would you choose? So that the difference between 1 upon n and 0 should be less than epsilon. What is this? N means 1 upon n.
Yes, sir.
What is your limit? Your limit is 0. Should be less than epsilon means less than this value. Now when this thing is less than this, give me that value n. Just you have to give me capital N, you are done. So give me this value so that I put that value here and difference between these two numbers should be smaller than 0.001. That's all.
Sir, here you are writing capital and small n. Means small n representing number of the sequences.
Sequence.
But what does mean for here capital N?
Capital N is a fixed value. Let's say 10,000. Small n is any value
Anyway.
after 10,000. You can take any value. Let me put here 10,000. 1 upon 10,000 becomes 0.0001. Let me do it. 1 upon 10,000 minus 0. This becomes 0.0001 minus 0. This is 0.0001. Is it less than 0.001? So let's say you name this value to be capital N, not n. But this n is any value bigger than capital N. If I write here this, will this be smaller than this?
Yes.
Obviously. If I write any other value beyond this, again smaller, smaller, and so on. So you give me a fixed value, and after this value, what happens? This difference is smaller than this. After that value. So this is what we call the mathematical definition in an example of convergence of a sequence. And if we are able to get this thing, it means we are on the right way to learn some mathematical definitions. And we call that this sequence is convergent to A when this thing is okay, when this thing holds. And we have different examples for the convergence of a sequence. Any question about this? First, we say that this sequence is convergent to 0. It means limit n goes to infinity, 1 upon n equals 0, and we will use this notation again and again. Limit n goes to infinity, 1 over n is going to be 0.